and relative extrema. And then it went through all the details on how you find your absolute extrema. So absolute extrema is your like very highest and lowest points, including the endpoints. So including -4 and 5, like so from here to here, what would be the absolute highest and lowest point? So your absolute max, the highest point is right here. And we would say that's at x equals 4. Just ask for the x value. And then your absolute min would be the very lowest point is at x equals 2. Okay, then it asks for relative extrema. So relative extrema usually does not include the endpoints. It can kind of go either way on that. You have to look at the directions, but we're just going to, like, for the purpose of this warm up, we're not going to include the endpoints. Relative extrema is where there's a high or low point anywhere on the graph. It doesn't have to be the highest or lowest, it just has to be a low or high point. So these two would be relative mins. So relative mins at x equals -3 and x equals 2. And then the relative max points here and here will be at x equals -1 and x equals 4. So relative max and mins are just like your high points and low points across the graph. And then your critical points is anywhere that the derivative is 0 or undefined. So your critical points, the derivative is 0 here and here. And then the derivative is undefined at the sharp points, which would be here and here. And so that would be x equals, it'd be -3, -1, 2, and 4. Question.
When you're doing the relative extrema, does that include your absolute extrema too?
Yep. So good question. So your relative max and min will already encompass your absolute max and min. Good question. Yep.
Can you explain why the endpoints wouldn't listed?
So I just verbally said it. It wasn't written on here, but usually for relative extrema, the directions will usually give you an open interval where you don't include the endpoints, and so that's why I did it that way. But if the direction specified you should include the endpoints, then you'd put them both on there. Yeah, it's just the directions didn't say clearly because this is just like a quick review. Okay, other questions?
So if it was included,
Then they'd be included. Endpoints would be right. Which most of the time for relative extrema they're not. That's why I didn't go through that. But on absolute max and min, they always are. Oh, one question.
So you include absolute maximum in the relative.
Yep. So absolute max and min also count as relative max and min. Yep. Good question. And just really quick, one more thing about the endpoints, since people were asking about the endpoints. The reason you always include endpoints in absolute max and min is because, like, let's say this graph went down here and then it stopped there. It's like this endpoint would be lower than that minimum. So like your endpoint can also count as the absolute max or min. And then relative extrema, they can also, but it just depends on what the directions say for the problem. Question.
so if the endpoint had an open circle, how would that work?
So you can't have a max or min at an open circle because you can't identify what that y value is there because it doesn't exist. And you couldn't be like, ooh, this is -5.99999. Like, you can't state it as a point. So a maximum or minimum has to be a defined point.
So I can't even I can't do any point above that.
Okay. And that's kind of, so the yesterday's notes talked about the extreme value theorem. For the extreme value theorem to work, your function has to be continuous. And so that's why the open circle also wouldn't work. Okay, so today's notes are not going to cover this. That was like yesterday's stuff. Today's notes are 2 more of our big theorems. So there's 5 big theorems during the year that we learn where you have to pretty much like word for word, you don't have to state it exactly, but it's got to be pretty close. You've got to have the same statement. So let's see if you recognize, do you remember IVT? It's been a while, but like IVT was one of them. And then squeeze theorem or sandwich theorem was one of them. We probably could stand to review that a little bit, I would say. And then extreme value theorem was in yesterday's notes. That just says a maximum and minimum will exist. And then the last 2 are today. And I say the last 2 because that doesn't mean we're done with calculus. It's just like there's the 5 big theorems we learned all have to do with limits and derivatives. And then the other stuff we do is just gonna be other stuff. It's just not theorems, it's other stuff. So today's two big theorems are mean value theorem and Rolle's theorem, and they're very close to each other. They relate a lot. So we do them on the same day. They have very similar sentences. This first one is you can abbreviate it MVT, like we used to have IVT. This one's MVT for mean value theorem. And what it says is if f of x is continuous on an interval from a to b, and I want you to notice it's like corner brackets or a closed interval from a to b, and differentiable from a to b, and that's open parentheses, so open bracket from a to b, then there exists a number where c is within or between the endpoints, so c is in between the endpoints, such that the slope, this is slope, equals the derivative at that point c. Another word for this is we could say average rate of change equals the instantaneous rate of change. And I'm going to show you a picture of what this means here in just a second, but I want to go over the words one more time, and then I'll explain to you a little more about what it means. So in the words, you have to state the function is continuous. That's been true of every single theorem we've learned, except for a squeeze theorem. But like we're used to like check to see this continuous. Then the new thing on this theorem that's different than the other theorems we've done is you also have to know that the function is differentiable. That means you can't have any sharp points. You can't have any vertical points. And then, of course, you can't have poles or asymptotes. And then as long as those two things are true, they're saying you can pick any 2 points on a graph and connect them together. Whatever slope you get there, that slope will equal the derivative somewhere. And that place C is in between A and B. And I'll show you a visual of that in a second, but that's kind of like what that wording is saying. Did you have a question before I show that?
So would that mean the instantaneous rate of change would be within a?
No, the value of C, the location of where the instantaneous rate of change occurs is in between A and B. Is that what you said? The rate of change would be in between A and B?
No, I was saying that if the instantaneous rate of change would be with.
No, the thing that's between A and B is the C value, the
Oh.
location where the instantaneous rate of change happens. Let's see. Okay, second one is called Rolle's theorem. We put your computer up, please. So Rolle's theorem is a special case of regular mean value theorem. So it says let f of x or let f be continuous. So that's the same, right? And be differentiable. That's the same. And again, it goes corner brackets, open parentheses. The part that's different is this theorem also has a third thing, f of a equals f of b. So I want you to like visualize in your head, f of a equals f of b. What does that mean? That means the two y values are the same. So you've got 2 points with the same y value. What would the slope between those 2 points be? 0. Good. Yeah, if you've got 2 points with the same y value, that slope between them would be 0. So on this part of the wording up here, where on mean value theorem, it's like the slope equals the derivative. Well, Rolle's theorem is like a special case of where the slope is going to be 0. So the derivative will equal 0 somewhere on the interval where C is between A and B. So it's very similar theorems. It's just that in the first case, the two y values are not the same y values. And in the second case, the two y values are the same. And the difference is that if the two y values are the same, you're going to put the derivative equal to 0 instead of the derivative equal to the slope. Below this is kind of like an explanation on like finding the slope between 2 points where the y values are the same. So Rolle's theorem is the same conclusion as mean value theorem. It's just that the slope between two y values that are the same would be 0. Okay, let's look at a visual of what I'm trying to explain with these theorems. Okay, so for mean value theorem. So mean value theorem gives you some sort of function. It'll be given to you in the directions, and you might know what the graph looks like and you might not. It's some sort of function. So the function given here, f of x, is like this cubic. Also in the directions will be an a and a b value. And at the a value and the b value, you look at those points and you connect them together and you get the slope. And you do that by doing f of b minus f of a over b minus a. So like that's the slope between those 2 points. And what the theorem is saying is as long as this is a continuous and differentiable function, then somewhere along here, if I was to consider every tangent line along this graph, like that at some point, one of the tangent lines will have the same slope as this one. And that's what this is showing, is that this tangent line at C has the same slope as that one. And C is going to be between A and B. Now, there can be more than one point. So in this case, there actually is more than one point. The other one's like over here. So that would be another value of C. Sometimes when we solve these, we'll have one answer. Sometimes we'll have multiple. It just depends on the situation. Question?
Is it okay if we think about it as just being parallel?
Yep, parallel, same. Yeah, parallel and same slope. I agree. Yeah. Yeah. Okay, and then Rolle's theorem, similar, is that you'll be given some sort of function. So this f of x probably is some sort of quadratic, and they'll give you an a value and a b value, and you check those two y values, connect them together, and find the slope. So the slope in this case happens to be 0. And then what that means is as long as you have a continuous and differentiable function, somewhere else, if I find all the tangent lines along this curve, there's going to be a slope of 0. And the location of that would be location C. Again, only works if this is continuous and differentiable. I want to give you a counter example. So like say you had an absolute value function. If I connect those two dots, that's a slope of 0. But in between there, if I draw all my tangent lines, I would never get a slope of 0, but that's because it's not differentiable. Like this theorem only will work if your function is continuous and differentiable. It's only guaranteed to work if it's continuous and differentiable. Question.
I know it's not differentiable on an absolute value function, but technically if you draw the tangent line, it would be flat.
It goes, the slope here is like say +1 and the slope here is -1, and there's never like a smooth changeover. It just flips from one to the other. If it's a curve, it would, like if it's curved. But that's why you can't take the derivative at a sharp point, because it just changes from one slope to the other slope instantly. Okay, we ready to try it? You'll look excited. Okay, we're going to start with A, and then just based on some questions my other classes have asked, we're going to go out of order today. But we're going to start at A. And try to write small, because we have math to do, and we have to write the sentences. Or if you want to grab another piece of paper, you're welcome to. Okay, so the directions say first, verify that the function satisfies the hypothesis of Rolle's and or mean value theorem. So let me go real quick. What is the hypothesis? That's the first part of the theorem. So that's the part where you check to see if the function is continuous or differentiable, and you check your f of a and f of b values. So like I'm going to check all three of those things. And if all three of those things work, then I do the conclusion, which is to state that the derivative equals the slope. And then last, we'll find all numbers C that satisfy the conclusion. Okay, so I'm going to show you all those things as we go. Quick side note before we do one of these is really quick. How do we tell if something is continuous? It's related. We're not going to do any piecewise functions on this. So we're not going to do like limits and the limit definition. We're just going to look to make sure our domain exists so that we don't have any holes or asymptotes. And the way you check domain is you look for a fraction or a square root or some sort of logarithm. And those are the three things we worry about as far as domain to make sure our function is continuous. So if you have a fraction, something divided by something, you take that the denominator can't be 0 because you can't divide by 0. So you only look at the denominator, make sure that you're not dividing by 0. If you have a square root of something, you take what's inside the square root symbol greater than or equal to 0. Not with the square root, just like the interior part, greater than or equal to 0. And if you have a logarithm of something, you take that something greater than 0. And then this all helps me find essentially my domain. And to tell if something is continuous, you look to see, does the domain exist on whatever interval I'm being questioned about. Okay, so let's consider that for part A. Okay, so I always like to kind of like section off to the side. I'm going to check my hypothesis first. So my hypothesis first, I'm going to check and see, is this function continuous from 0 to 2 with closed brackets? So to check to see if it's continuous, I look at the f of x I've been given, and I look to say, are there any fractions, square roots, or logarithms? And there's not. So that means my function is continuous from 0 to 2. So yes, I'm good there. Okay. Is my function differentiable? Open brackets, 0 to 2. So to check differentiable, you're going to do the derivative. So actually, I'm going to have to show that math. The derivative is a power rule. It's 3x squared minus 6x plus 2. And then to check if the function is differentiable, I do the same thing. I'm looking to see, is the derivative continuous? Does the derivative have a domain that exists from 0 all the way to 2? And so I look at my derivative. So does my derivative have a fraction or a square root or a logarithm? And it does not. So we're good here. And then I'm going to check my f of a and f of b. And it's not saying f prime of a and f prime of b. I'm plugging 0 and 2 into the original up here. So I plug in 0 and I get 0, 0, 0 plus 5 is 5. And I plug in 2 and you guys check math behind me. I get 8 minus 12 is negative 4. Plus 4 is 0 plus 5 is 5. By the way, quick side note, you might need a calculator on some of these problems because the decimals do get a little, or like the numbers get a little crazy in some places, but like that one's not too bad so far. So right now I'm checking the hypothesis. I'm checking just, is it continuous, differentiable, and I'm looking at f of a and f of b. It is continuous, it is differentiable. Then I use this to decide if I'm going to do mean value theorem or Rolle's. Rolle's theorem works if these are the same y values, which it is. So this one's going to be Rolle's theorem. Okay, so I write the sentence for Rolle's theorem, which you've got there on the left, and you've got to write your sentence. It doesn't have to be exactly the same, but it does have to have the same meaning to it. So my sentence is going to be something like this: f of x is continuous on the interval close bracket at 0 to 2. And differentiable on the open bracket 0 to 2. And f of 0 equals f of 5. Sorry, f of 2. Sorry. F of 0 equals f of 2. So therefore, or so, or then, like whichever word you want to do, the conclusion says, so f prime of c will equal 0, where c is between 0 and 2. Yes, question. Why did we do it? That's what the theorem. If you look up at your theorem, go back to it again. It's got closed bracket for continuous and then open bracket for differentiable. Just because we're writing down like the exact, we're essentially copying the theorem down, but with our numbers for our problem. Yes, question.
Do you put closed interval or open interval, like the last part?
The 0 to 2 is open. Okay, so you get your sentence written. Question. It is parentheses. We'll practice one. We'll do it that way too, so you can see it. Okay, then, so we've done the like hypothesis and conclusion where it says final number C. That's where then we solve that part of this. So we take the derivative that I've already got, equal to 0, I'm gonna solve it. And then my answers should be between 0 and 2, or I made a mistake. So take the derivative I already got. I'm gonna go through and solve that and figure out what numbers are like, what's the location, what's the x value where my cubic has a slope of 0. That's what I'm looking for. So this is derivative equal to 0. Okay. And I'm looking at this as factors. So if you multiply it, like what multiplies to 6 and adds to -6, I don't think there are any numbers that do that. It's like 6 and 1 would add to 7 and 5, or 2 and 3 would add to 5 or 1. What do we do if we can't factor? Yeah, look at you guys. Oh, we have not done this in ages. Oh, here's a nice little review. If you can't factor, you gotta do quadratic formula. Okay, we can do it. Now you've done so much calculus, this should seem easy. Okay, quadratic formula is opposite of b. So it's gonna be 6 and then plus or minus. B squared is 36. Minus 4ac is minus 4 times 3 times 2. All over 2a is going to be 2 times 3. So that's 6 plus or minus square root. 4 times 3 is 12, times 2 is 24. So 36 minus 24 is 12. And then you can't cancel those 6's because you have to cancel in all 3 terms. So I can't cancel that out. I could reduce the radical 12 a little bit and make this 2 radical 3 by pulling out the perfect square of 4. And now you can cancel a little bit. You could do 2, 2, and 2. Like you could take a 2 out of everywhere. So 3 plus or minus radical 3 all over 3. Well, it's not letting me write it. Not letting me write it down. Where did that all just go? Is it just gone? Okay, so I was trying to like 3 plus or minus radical 3 over 3. Did y'all get that much? Sorry, I don't know how I did that just now, but I can't write it all. Where did my I don't know what this is. Let's see. No. Did I lose? I had like a pencil symbol thing. Does anyone see it up here? Maybe if I take it out of this or like, how do I get out of this? Maybe go to that. Where is it? Down here, this thing? Not that. Wait, okay, show me. Sorry. Oh, maybe this one? Oh, that's it. Oh, this is gonna be really sad if I can't write up here anymore. I feel like none of those are gonna give me. Oh, that worked. Okay, thank you. Erase that? Is that eraser? How do I erase? Why did this all just change?
Maybe if you click on the scribble, there'll be a eraser button. So. Wait, there is one at the bottom.
I know that's a highlighter. Oh, what? Oh my gosh. Technical difficulties. I don't know. Okay. This one. I don't know. Okay. I'm gonna do the best I can here. Okay, so jump down to E, please. E. Okay, so we're gonna start out with continuous, differentiable, and f of a and f of b. So like off to the side, I'm thinking about continuous, closed interval 1 to 4. Like that's what I'm trying to decide. Okay, so to decide, I look and say, do I have a fraction or a square root or a logarithm? And I do have a fraction. So I take the denominator of the fraction and I say that can't be 0. And if I solve, I get that x can't be -2. Okay, so now let me look at my interval. My interval says 1 to 4. And my place where I have an asymptote is at -2. So on my graph, if -2 is an asymptote, but I'm not looking at -2, I'm only considering 1 to 4, this actually passes the test still. That's like a check mark. Sorry, I don't know why that's supposed to be a check mark. So it does pass the continuity because the discontinuity is at -2, which is not in between 1 and 4. Okay, so now I check to see, is this differentiable from open interval 1 to 4? So to check to see if it's differentiable, I have to find the derivative. And that's a quotient rule. So I'm going to do low d high. So x plus 2 times 1 minus high d low over low low. And then at top, my x's are going to cancel, so I have 2 over x plus 2 squared. So now I'm looking at the derivative and I ask myself the same question. So I have a fraction, a square root, or a logarithm. And in this case, I still have a fraction. So I take the denominator of my fraction and I say that that can't be 0. Square root on both sides. And I get still that x can't be -2. So -2 is not on my interval between 1 and 4. So I actually am going to pass this test also. Now, had I solved this and I come up with like x can't be 3, then I would have had a problem and I would have said does not apply. Like neither theorem works, can't do it, done. Thanks for the short problem. But of course, they're all going to work. At least the ones in our notes will work. Okay, so I know that the theorem is going to at least apply. Now let me check my a and my b values. So I'm going to do f of a and f of b is f of 1 and f of 4. So if I plug in 1 to the original up here, I get 1/3. And if I plug in 4, I get 4 over 6, which is 2/3. Okay, should I do mean value theorem or rules? Mean value theorem, good, yes, why?
Because they don't.
They're not the same, they're not equal, good, okay, so I'm gonna use mean value theorem. So maybe if you might have to flip to the other side, remind yourself of what that sentence looks like. I guess I'll write my sentence over here. So f of x is continuous on the closed interval from 0 to 2. Sorry, 1 to 4. What was 0 to 2? That is the last one?
Yeah.
Sorry, from 1 to 4. Scribble, thank you. Okay, and then and f of x is differentiable. Nope, f of x is differentiable is the same thing as saying f prime is continuous, which is weird. Like, I know that's kind of weird, but. And so we don't have to say anything about f of a or f of b being equal because we're not using rules. So I'm just going to go on to the rest of this and say, so f prime of c equals, and then I do the slope this time. So I do f of b minus f of a over b minus a. So that's going to be 1/3 over 3, which I'm a little out of space here, so I'm going to reduce that as 1/9. Where c is between 1 and 4. And I've used this symbol for between this time just to like mix it up a little. So my sentence says the derivative will equal 1/9. The last part of our directions are identify the C values that make the statement true. So I'm trying to figure out where would my slope be 1/9. And whatever that number is, it's going to be between 1 and 4. So I'm going to go back to the derivative I've already calculated and put it equal to 1/9 and solve. So 2 over x plus 2 squared equals 1/9. And cross multiply, I get 18 equals x plus 2 squared. Square root on both sides, plus or minus radical 18. You could make that a 3 radical 2 if you like, and then subtract 2 on both sides. So I get -2 plus or minus radical 18. And then I only want to keep the answers that are between 1 and 4. So if I do -2 minus radical 18, that's going to be something very negative. And I only want answers between 1 and 4. So it's going to be -2 plus radical 18 is your only C value that works. And if you have a calculator right there, you're welcome to like plug that in. Oh, I should have said that for the last one. On the last one, the 3 plus or minus radical 3 over 3. Both of those decimals worked. They were both in between 0 and 2. And in this case, there's just only one that's between 1 and 4.
Where'd you get the 18? It's like,
From cross multiply.
um,
So you do want to check in the end, like, do you want to type in a calculator or just like estimate in your head which ones are actually on the interval between 1 and 4? See if I can find a way to delete this. Okay, let's go back and do the square root one. Yeah, we'll do square root and then cube root and then the trig one. Oh no, did I lose the scribble? Oh yeah, I gotta change it to this. Okay. Okay, so first thing I'm checking is, do we have something that's continuous? Then is it differentiable? And then FA and FB. So I'm checking right now, continuous from -6 to 0. That's what I'm gonna look up first. Okay, so to check for continuity, it's the same thing as checking for domain. I'll look for a square root, fraction, logarithm. In this case, have square root. So I take what's inside the square root, greater than or equal to 0, and solve. And that tells me the domain that exists on this graph, and therefore where the function is continuous on this graph. And hey, it's continuous from -6 on. So we're good because my interval starts at -6 and goes up. If my interval was -10 to 0, that would have been a problem, but it starts at -6, so we're good. So is it continuous? Yes. Is it differentiable? Open interval, -6 to 0. The way you check that is you've got to do the derivative. The derivative on this one is a little more involved because we have a product rule and a chain rule. So we do A, B prime is going to be X times 1/2 X plus 6 to the -1/2. Chain on the derivative of the inside, which is 1. Plus A prime B is going to be 1 times X plus 6 to the 1/2. And then I'll just go through and simplify that. So I get X over 2 radical X plus 6 plus 1 over radical X plus 6. Oh, sorry, I messed that up. It's not 1 over. That was a positive. I've got a glare right there. Hold on. Sorry, it's just X plus 6 to the +1/2. So square root X plus 6. And then I want to put that over 1 and do a common denominator. So I multiply by 2 radical X plus 6 top and bottom. So my denominator is 2 radical x plus 6. In the numerator, I just carry down that x, and then when I multiply the square roots together, they cancel out. So I just have 2 parentheses x plus 6. So overall, 3x plus 12 over 2 radical x plus 6. Okay, so lots of work to get my derivative. Right now, what I'm trying to do is figure out, is my function differentiable? Do I have a fraction, square root, or a logarithm? Well, I have a fraction and I have a square root. So I did both. So I can take the inside of the square root greater than or equal to 0. However, my square root is within the denominator. See how the square root's in the denominator? So at the same time, I've also got to think about the fact that this denominator also can't be 0. So I'm really going to take the inside of my square root instead of greater than or equal to 0, since I don't want it to be 0. And I'm just going to do greater than 0. Okay, let me say that again. So I see some confused faces. Okay, so normally you take the inside of the square root greater than or equal to 0. Like that's what we did up here. That's fine, no problem. But now my square root's in a denominator. And that means I have 2 rules to consider at the same time. I've got the fact that it's the bottom of a fraction and the fact that it's a square root. So not only do I want my square root to have a positive input, but I also don't want my denominator to be 0. So I also have to consider that and not put the equal to. Because if I end up with a square root of 0 on the bottom, then I would get something undefined. So that's why I'm taking out the equal to. And then this just gives me my function would be defined everywhere greater than -6, not at -6, because at -6, my denominator would be messed up. So only greater than -6. So this one barely, squeaks by, barely passes because the brackets change for the differentiable part. And then I'm going to check my f of a and f of b. So f of -6 and f of 0. If I plug in -6 to this part, I'm going to get 0. So x times 0 is just 0. I guess it would be -6 times 0 will still be 0. Then if I plug 0 into this part, I get 0 times square root 6, which is 0. Okay, which sentence do I write? Will I use mean value theorem or Rolle's? Rolle's, very good. Okay, good. Okay, so f of x is continuous on the interval from -6 to 0 and differentiable on the open interval -6 to 0, and f of -6 equals f of 0. And so Rolle's theorem says f prime of c will equal 0, where c is between -6 and 0. So I've got my sentence written, then the last thing I will do is actually solve this part out. I'm going to take the derivative, which I've already done. Put that equal to 0 and solve it. And then check to make sure that I just keep the answers that are between -6 and 0. So I'm going to multiply both sides by the denominator, and that will just cancel the denominator out. And then subtract 12, divide by 3, x is -4. And by the way, I'm okay with you putting c equals or x equals. But that number is between -6 and 0.
From College Board at Berkeley's, would they also accept X?
I think so. It's a good question. So the question is like, will College Board accept X equals, or would you have to put C equals? If this was a College Board question, I probably would use their letter, but I would just like somewhere in there show that C and X are equal to each other, and then you could use either. Like X equals C, like they're all referring to X values. C is just a specific X value. Okay, let's do the cube root one. All right, so cube root and square root are not the same. You do not have to check to see if a cube root is greater than or equal to 0. Like you don't have to do the inside part because you can take cube root of negative numbers. So there's not a domain restriction on cube root. That makes our work a little bit easier. So when I'm checking continuous and differentiable, I want to see if I have a fraction or a square root or a logarithm, and I don't have any of those. So this is good to go. And then to check differentiable, I have to take the derivative first and see if that has any fractions or square roots or logarithms. So think of this as a 1/3 power. My derivative is 1/3 x to the -2/3. And so negative power, I move down to the bottom. And then, oh, now I have a fraction. So I'm looking for a fraction, square root, logarithm. Fraction, the denominator can't be 0. So I'm taking the denominator and saying that that can't be 0. So I divide by 3 on both sides. And then do both sides to a 3/2 power. And I get that x can't be 0.
Would we have to show all this work on effort to, we just like use logic and say that?
I think you could go from this step to this step. Without, I'm just trying to make sure everyone understands what to do with that exponent, but yeah, you don't have to write that middle step, I would say. Okay, differentiable passes. This is another one that barely squeaks by because 0 is no longer included in the interval, and 0 would have given us a problem. So it barely works. And then I'm going to check f of 0 and f of 1. If I plug 0 into the original, I get cube root of 0, which is 0. And if I plug 1 into the original, I get 1. And so it has to be mean value theorem because they're different numbers. The y values are different. Okay, so that sentence is f of x is continuous on the closed interval 0 to 1 and differentiable on the open interval 0 to 1. And the two y values are not the same. So then I just go ahead and say the derivative will equal the slope. So I do f of b minus f of a over b minus a, which works out to be 1, where c is between 0 and 1. And then the last part of this is I just solve my equation. I've got to take the derivative equal to 1 and solve it. I've already done my derivative. If I put that equal to 1, I multiply both sides by 3x to the 2/3. And then I'm going to divide by 3. And raise both sides to the 3/2 power. And then again, I don't have a calculator in front of me, but whatever this decimal is, it must be between 0 and 1 because otherwise the theorem wouldn't have applied. Okay, I can tell I'm losing it. Can we do one more so we're at a good break point and then we can do a little break? We're getting sleepy. I can see it. Okay, let's go to this one. So sine and cosine are both continuous graphs. And I think you could probably, oh, this is such a pain. I gotta figure out how to fix this. I think you could probably like visualize your sine and cosine graphs and just convince yourself that it's continuous. But also because sine and cosine don't have a fraction, square root, or logarithm. Now, tangent does have a fraction. Tangent is sine over cosine. But sine and cosine don't have a fraction or square root or logarithm. So this is easy to say, yes, this is continuous from -1 to 1. Yes. And then for differentiable, I take the derivative and see. So my derivative here, the angle is 2 pi x. You have to chain on the derivative of the angle. So derivative of the outside is cosine. And if I chain on the derivative of the angle, I'll get 2 pi cosine of 2 pi x. So now I look at the derivative equation and ask myself, does that have a fraction, square root, or logarithm? Which it does not. So we're good there. Then I do f of -1 and f of 1 and see what I get. So f of -1, if I plug -1 in here for x, that's the same thing as sine of -2 pi. Okay. Quick reminder, what is sine of -2 pi? 0. Good job. Oh, I knew that. That's quick. Good. It is 0. Yeah. So as a reminder real quick, so like this is an angle of 0, -2 pi would just go in the opposite direction. And cosine sine value is 0. And then f of +1, if I plug +1 in here, I would get sine of just 2 pi. So that's starting here, now going 2 pi in the positive direction. I just end up back in the same spot. I still get 0. Okay, is it mean value theorem or Rolle's? Yes. Okay, so Rolle's theorem, I'll write that sentence. F of x is continuous from -1 to 1 and differentiable from -1 to 1. And f of -1 equals f of 1. So the derivative will equal 0 where c is between -1 and 1. Okay, so then to solve that part, I take the derivative I've already done and put that equal to 0 in this case, because I'm solving the Rolle's theorem, which is equal to 0. Divide both sides by 2 pi. Ooh, then it gets tricky real quick. So that these are easy to mess up. Remember, if you have a coefficient here in your angle, like just ignore that. You do that at the end. Just ignore that. And I'm looking at where does cosine equal 0. So think on your unit circle. So sine equals 0 here. Cosine equals 0 up here, which is 3 pi over 2. And down here, which is 5 pi over 2. And all of the multiples of that. So I'm going to write it like this. 2 pi x equals. There's an infinite number of places, but I'm going to start at -5 pi over 2. -3 pi over 2. Yes. Yes.
I'm just
Okay.
confused
Still
from
going. Okay.
-5 pi.
Okay. I know. I didn't say it. I wrote it and I didn't say it. I'll show you just a second. Okay. I'm on 5 pi over 2. I think I touched this. Oh. Okay, I'm not gonna be able to fit it in here. I'll just do a little caret, 5 pi over 2. Okay. All right. Where did the 5 pi over 2 come from? is from. So this is a place, so this is pi over 2. And if I keep going, it'd be 3 pi over 2. If I keep going, it'd be 5 pi over 2, and then 7 pi over 2, 9 pi over 2. So it's like an infinite list of numbers. So this is like dot, 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 dot. But because I have a negative up here, I also wanted to consider going the other direction. So it'd be like negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, negative 7 pi over 2. Like I'm listing out all the possible ones. And then I'm only going to keep, in the end, I'm only going to keep the ones between -1 and 1. So hopefully I made my number, like my list of numbers big enough. In fact, I think I made it too big, but. So that gives me all the possibilities. Then I have to divide both sides by 2 pi to get x by itself. Now just, the ones with the angle are tough. Okay, so I've got to divide by 2 pi. Dividing by 2 pi just puts a 2 pi in the denominator of each of these. So think about it for a second. So if I put 2 pi in the denominator here, the pi's will cancel and I'll get a 4. Okay? If I put 2 pi in the denominator here, the pi's will cancel and I get a 4. If I put 2 pi in the denominator here, the pi's will cancel and I'll get a 4. And same thing, put 2 pi in the denominator here, pi's will cancel, and I'll get positive 1/4, and then positive 3/4, and then positive 5/4. But I'm only going to keep the ones between -1 and 1. So I did make my list too big. I'm just going to keep these ones. If you're like, oh my gosh, why are there so many answers? Like, why are there so many on this one? Well, a sine or a cosine graph is probably going to have a lot of places where the slope equals 0. There's a lot of little like max and midpoints.
Would you be acceptable to just put plus or minus 3, 4, plus?
Yeah. Okay, quick break. Just quick though, because we have a lot today. So if you want to just stand up for a second and wake yourself up. Move your body a little bit. Did all of these, right? Okay, so we're here. Okay, let's go ahead and move on. I know that's not a lot of time. We have a lot today. Okay, hope you're a little more awake. Okay, to be totally honest with you, these next 3, we don't have time to fully work these out and work out the delta math type ones. So I'm going to just quickly like discuss these just for a second and like breeze over them so you can understand the concept. And then I want to look at like the gray boxes. Those are the delta math ones are like your homework. I want to make sure we address that. And then we still have our FRQ at the end. So like we just have a lot to do. So these 3, I'm not going to go through fully, but I just want you to think about them. Okay. So the wording on number 2 is kind of crazy. It says f of x equals x minus 1 to the -2. Show that f of 0 equals f of 2, but there's no number c such that the derivative equals 0. So they're saying like, okay, the 2 y values are the same, but the derivative doesn't equal 0. Like, how could that possibly be? Because Rolle's theorem says if the 2 y values are the same, the slope between them would be 0. Therefore, your derivative would be 0. But there's 2 things you got to check first. What are the 2 things we check first? Continuity, differentiability. Good. Okay, so what's going on with this? That's a fraction. It doesn't look like it, but it is. That's a fraction. So if you rewrite this, you'll see, oh, that function is not defined at 1. So it's not continuous at 1. Therefore, Rolle's theorem doesn't apply. So we haven't broken the rule, but it says like, why does this not contradict? Well, we didn't break the rule because the rule says if the function is continuous and differentiable, then there would be a place where the slope is 0. But since it's not continuous, it's not going to work. It's not going to be guaranteed. So it does not break the rule. Okay, and then like I said, quickly, the second one.
Wait, so it doesn't break the rule
because the rule doesn't apply. So the function is not continuous at x equals 1. And so that means you just can't use the rule. Denominator equal to 0. Oh. Okay, then number 3, so this one says like at 2 o'clock, speedometer is 30 miles an hour. At 2:10, it's 50 miles an hour. Show that at sometime between 2 o'clock and 2:10, the acceleration is exactly 120 miles an hour. So kind of interesting, like application. There's nothing that gives you the actual function here. There's no equation. You just have your A and B value, and your A and B value are the times. Okay, so what we have there then, is a function that we have to decide on our own. Would the speedometer make a continuous graph? Like, would it be possible for your speed to go up and have an asymptote go into infinity? I mean, not in real life, right? Like maybe in the movies or something, but like you cannot travel an infinite speed. So just like practical application, your speed would be continuous and differentiable. Okay, so there's not, the wording in here doesn't say it. You just have to imply from the context of the situation, the function would be continuous, would be differentiable, and then you do the slope. And so we're recording an hour, so like 1/6 of an hour has passed because 10 minutes has gone by. So if you just do y2 minus y1 or x2 minus x1, you get the 120. But that one is just like kind of in context. Question?
How would we,
It would be 10 minutes, which is 1/6 of an hour. Like, so when you do y2 minus y1 over like the 10 minutes, you get 20 over 1/6 of an hour gives you the 120. And so your theorem says if the average rate of change is 120, then the actual derivative is 120. The real world scenarios you'll be given, it'll say in the directions that it'll say the words in the directions. That's just that we're kind of breezing over these. I know we're doing these like faster because we're out of time. But yeah, it would say it in the directions. Most of the time it just says the word differentiable, which actually means both are true. Yeah, because 10 minutes would be 1/6 of an hour. Yep. Okay, well, you guys answer for me. Does anyone know? So number 4, like, why would you not be able to do mean value theorem on that one? Anyone know? Sharp turn. Yep. Okay. So sharp point. Excellent. So sharp point. Where's the sharp point at? Is that 1? Yeah. So take your absolute value to the right one. So it would not work because this function is not differentiable at x equals 1. So not differentiable. Okay. So here's these last 3, we can kind of go through them fairly quickly, but I want you to understand the logic that this is what your homework's like. So Delta Math, they're going to give you some information in the directions. You're going to check on your end. You're going to check 3 things. You're going to check continuity, differentiability, and the slope. Okay. Like those are the 3 things you're going to check. If your function is continuous and differentiable and you find a slope in the table, that's the same as the slope in the directions, then like all of those, like that will go together. Your function is continuous and differentiable, therefore the slope must equal the derivative. But if you get a place where the slope doesn't equal, then that means one of your first 2 things must not have been true. And it's confusing to think of. So let me go through some of these scenarios. Okay, so selected values of the function f are shown in the table. The function is continuous. Okay, so that's important. So we have continuous. Now I don't see anything about the word differentiable. So all I have right now is continuous. Okay, then I'm going to look at the table. So I'm going to pause. I'm reading this paragraph for a second. I'm going to look at the table and see if I can come up with a slope of -5/2 anywhere. Okay, okay, so I get -5. So I can check these 2 or these 2 or these 2. -11 minus -6 would be +6 over there minus -2. Okay, I get -5/2. Okay. Okay, I found a place on the table where my slope is -5/2. Okay, so when I look at the directions, it says, hey, by the way, on the actual equation, I never get 5/2. See that word not? So the directions are saying I have this continuous function and the slope is never -5/2. But when you do your table, you get -5/2. So that means the function is not differentiable. Because had the function been continuous and differentiable, my slope on the function would have equaled my slope on the table. And it doesn't work. It's telling me I don't get this slope. Therefore, the original function is not differentiable. Because if it was, these two things would have equaled. So when it says then determine the validity of this statement, the function is differentiable? No, false. Because if the function was continuous and the function was differentiable, then any slope I come up with in this table would also exist on the derivative. But it tells me in the directions, the derivative doesn't equal that slope.
So that makes the statement false.
So that makes the differentiable part false.
Oh, okay.
Because they're saying determine if the statement is true or false. So like the function is differentiable. Well, it can't be because the slope on the table doesn't ever show up in the slope on the original. And it would have had to if it was continuous and differentiable. Since that slope didn't show up because it says not, like that slope didn't show up on the original function, then it must not have been continuous and differentiable to begin with. It's a weird backwards way of thinking. They're not all backwards like this. I'm just showing you some of the examples that you might see. Okay, so that's one type. Okay, next one. Okay, so on this one says, oh, also, oh, it's continuous and differentiable this time. Okay, so it's continuous and differentiable. Now I'm gonna look at my table and say, is there anywhere where the slope is 4? So let me check and see either here or here or here. Oh, I can't do all these negatives in my head. Okay, so I get 4/1. Oh yeah, okay. I get 4 with the first two. So I'm told my function is continuous, my function is differentiable, and there's a place in my table where the average rate of change is 4. Well, mean value theorem says as long as your function is continuous and differentiable, your average rate of change is going to equal the derivative. It's guaranteed that that will happen. So this would be a true statement. Yes.
Was there ever be an instance where you still could be either true or false?
Yeah, that's where we're looking next. Okay. So is there a time where like you can't tell? And that's what this one is. Now who's giving away the answer? Okay, that's all right. All right. So okay, so now we're told on this one, the function is continuous. Okay, and then it says there exists a value C. Okay, so I'm looking to see, does the slope ever come out to be 13/3? Okay, so I think it's from here to here. Okay, so I'm able to get the same slope. But the question is, would this always be guaranteed true? And the only way for it always to be guaranteed true, that your average rate of change will equal your derivative in one place, is if you also had the word differentiable. But it doesn't have the word differentiable. So it's a nice coincidence that we did get the same slope. But I can't guarantee that that slope occurs. So this is could be either. If they added the word differentiable in the directions, it would be a this. If they gave you a slope, didn't occur, it would be this. Like, it's weird to think through these. The logic, it's weird. It's like logic.
So if the slope that we just got, like none of them match the slope that they gave us.
Then you wouldn't know either. You couldn't tell true or false, because then you don't know any information.
Yeah.
Like you hardly know anything. So it could be, I don't know. The only thing that guarantees is if it's continuous and differentiable, that any slope here will occur on the derivative. Okay, I know those are hard to think through, and that's like gonna be our homework tonight, so work on those. Your homework tonight is to like finish Friday stuff. And then we got delta math for both days and WebAssign on both days. So we got some calculus stuff to work on tonight. Okay, for our last 15 minutes, I'm gonna say this and no one's gonna listen. Don't flip this page over. Didn't that make you just want to go? That's the answers. Okay, so honesty policy, I'm gonna put a 15-minute timer up. I want you to have the experience of, I want you to work with a partner, okay? This is an FRQ. It actually uses the stuff we learned today and some old stuff. So I want you to spend 15 minutes, work as hard as you can with a partner. 15 minutes is the cap on time, okay? When you finish, you can flip it over and check, but try not to check it as you go. Try to like invest just 15 minutes of time at the most to get what it's like to have that time and then flip it over and check it. Okay. Do we even have 15 minutes? We have like 12 minutes left. So do the best you can in that 12 minutes.
So.
You're not gonna go over the answers today, are you?
And